Most audiophiles have been looking at DACs completely backwards. We obsess over the chip inside, ESS, AKM, Burr-Brown, as if that one component is responsible for 100% of the sound. Reviews, comparisons, charts, spec wars, all pointing you to the same conclusion. Better chip equals better sound. But here's the twist. Two DACs using the exact same chip can sound completely different. One warm and holographic, and the other thin and sterile. So, what's actually causing the difference? It isn't the chip, it's the part almost nobody talks about, and it has more influence over your sound than any ESS or AKM ever will. In today's video, let's go deeper into the part of the DAC that never makes the headlines, the analog output stage, the true architect of a DAC's sound. We're going beyond the chip to uncover why this quiet, often overlooked section of circuitry has more impact on your music than any DAC chip ever will. You're about to learn what really matters. All right, let's set a baseline. The digital to analog converter chip, the famous DAC chip, absolutely has a critical job. It's the very first step in liberating your music from its digital prison, so to speak. For years, we've been caught in the crossfire of the spec sheet wars. Manufacturers proudly display the number of the latest chip from ESS, AKM, or Texas Instruments, Burr-Brown's line. They boast about staggering numbers, total harmonic distortion plus noise, figures with an almost comical number of zeros after the first decimal point. So, what does this chip do? In simple terms, the DAC chip is like a hyper-fast, incredibly precise musician reading sheet music. The digital file, your ones and zeros, is that sheet music. The chip reads this binary code and translates it into a corresponding analog voltage level. It plots out the points of an analog waveform by making millions of calculations per second. It's easy to see why the whole audio industry got obsessed with this one part. The chip is quantifiable. It's a single part number you can point to. Its performance can be measured in a lab and shown in neat, tidy graphs. A DAC with an ESS Sabre ES90338 Pro chip just seems better than the one with an older chip. It's a simple marketable story, right? It makes comparing two DACs feel as easy as comparing two cars by their horsepower. But this is where the official story starts to fall apart. Knowing a car's horsepower tells you nothing about its transmission, suspension, tires, or the driver's skill. And in audio, the DAC chip is just the engine. It provides the raw potential, but that raw potential on its own is completely useless. The signal that comes directly out of that miraculous high-spec chip is fragile, weak, and in a format that your amplifier can't use. This focus on the chip has created the chasing of numbers, believing that this lower distortion and higher bit depth are the only paths to audio nirvana. They buy a DAC with a flagship chip, plug it in, and sometimes they feel underwhelmed. Something is missing. The sound might be clean, but it's sterile, detailed, but cold. It lacks soul, body, and that indescribable thing we call musicality. The reason for that disappointment isn't in the chip. It's everything that happens after the chip. It's the parts that don't have a flashy logo or a simple number to market. So if the DAC chip is just reading the sheet music, who then's actually playing the instrument? That, my friends, brings us to the analog output stage. The analog output stage is all the circuitry that sits right after the DAC chip. Its job is to make that raw, weak, and frankly unusable signal from the chip and turn it into a clean, stable, and powerful signal that your preamp or amplifier can actually use. This stage has two fundamental jobs. Get these two, and you'll unlock the whole mystery. First, and most critically, is a process called IV conversion, for current to voltage conversion. Here's a secret most manufacturers don't explain. Many high performance DAC chips, especially ESS Sabre and some AKM models, don't actually output a voltage signal, they output a current signal. Other designs, like many Burr-Brown and Cirrus Logic chips, do output voltage directly. But in high-end DACs, current output chips are common because they give designers more control in the analog stage. The problem is the preamp or integrated amp expects a voltage signal. A current signal is useless to an amp. It's like trying to fuel a gasoline car with crude oil. The IV conversion stage is the refinery. It's the essential translator that converts the DAC chip's current into voltage the rest of your system understands. This is where the signal is most delicate. Any noise or distortion introduced here gets permanently baked into the sound and then amplified by everything down the line. A poorly designed IV stage can cripple the performance of the most expensive DAC chip, killing clarity, precision, and musicality. Second, once the signal is converted to voltage, it's incredibly weak. It doesn't have the signal to travel down a cable and drive your amp without serious degradation. So, the next job of the output stage is to be a buffer and an amplifier. It gives the signal its first shot of gain, making it robust and stable. It also creates a low impedance, which is crucial for a signal to transfer to the next component in your chain. This two-part process is where the magic happens. This is where the artistry of the DAC designer truly shines, because how they do these two things defines the final sound far more than the chip itself. This is where a manufacturer dials in their house sound. Is it warm and smooth, or sharp and analytical, vast and spacious, or direct and intimate? Those qualities aren't born in the digital world of ones and zeros. They are sculpted right here in the analog output stage. The DAC chip provides the essential ingredients. The output stage is the master chef who actually creates the dish. Okay, once we accept that the analog output stage is the true sculptor of sound, we hit a major fork in the road of design philosophy. When an engineer builds this critical section, they face a choice that has defined a decades-long debate. Do they use an integrated circuit known as an op amp, or do they build the circuit from the ground up using individual components, a method known as discrete design? This choice has huge implications for the cost, the complexity, and ultimately the sound of the DAC. Let's start with the most common approach, the operational amplifier or op amp. An op amp is a complete amplifier circuit shrunk down into a tiny silicon chip. It's a marvel of engineering, a small 8-pin part that does a job that once took a whole board of components. From an engineering view, using op amps is a logical choice. They are cost effective and small, which means smaller, more affordable products. They also offer incredible consistency. Because they're mass produced, the tolerances are tight and the performance is predictable. On a spec sheet, op amps can deliver amazing measurements, extremely low noise and distortion. They are the textbook perfect solution. If your goal is the best possible numbers on an audio analyzer, a good op amp is often the most direct path. So, what's the catch? Why doesn't every high end DAC just use them? The critique is usually about sonic character, not measured performance. While op amps are technically brilliant, they are jacks of all trades. Some listeners describe the sound of certain op amp circuits as being a bit clinical, sterile, or lacking that last bit of natural emotional engagement. They might measure perfectly, but sound just a bit lifeless. An op amp is like a world class factory built engine. It's reliable, efficient, and exceeds every metric on paper. It will do its job flawlessly, but it might lack the bespoke character and hand built soul of an engine crafted by an artisan for a specific race car. And that brings us to the other side, discrete circuitry. A discrete output stage tosses out the all in one chip. Instead, the designer builds the entire amplifier circuit from scratch using individual hand selected parts, separate transistors, resistors, capacitors, and diodes. The main advantage here is one word: freedom. The designer has total control over every aspect of the circuit. They aren't limited by an op amp's internal design. They can pick transistors known for their sound, use oversized, high quality resistors, and run the circuit at much higher idle current, often what's called Class A operation. Running in Class A means the transistors are always on, which can dramatically improve how the circuit handles sudden musical peaks, resulting in better dynamics and transient response. Of course, this approach has its own challenges. Discrete circuits are far more complex, take up more space, and are much more expensive to make. It's a labor intensive and frankly an art form. Sonically, well made discrete circuits are often praised for things that are harder to measure: refinement, naturalness, and musicality. They can present a soundstage with more depth and air and deliver a more holographic presentation that many find more engaging. This is the hand built race engine. It's expensive and temperamental, but it's built for one purpose: to deliver the most exhilarating performance possible with a character a mass produced unit cannot replicate. But remember, discrete isn't automatically better. A poorly designed discrete circuit can easily be beaten by a high quality op amp that's been skillfully implemented. The devil's in the details. But when you see a manufacturer advertising their fully discrete Class A output stage, you now know what they mean. They're signaling that they've chosen the harder, more expensive path in pursuit of a specific goal. Now, beyond the big debate over op amps and discrete circuits, there is a supporting cast of components that are just as critical to the final sound. These are the true unsung heroes of the output stage. A designer can use the finest parts, but if they neglect these foundational elements, the whole thing falls apart. Now, let's revisit that IV conversion stage because its importance cannot be overstated. As the very first analog block after the DAC chip, it's the most vulnerable part of the signal path. Any little bit of noise or distortion that gets in here doesn't just get passed along, it gets amplified. It's like a tiny flaw at the start of a photo enlargement process. By the time you see the final print, that tiny flaw is a giant blemish. This is why high end designers obsess over the IV stage, often using their most sophisticated circuits right here to preserve the integrity of that initial translation. The sonic result is a blacker background, allowing you to hear the most delicate details of a recording. Next up is the analog filter stage. The digital to analog conversion process creates unwanted high frequency noise. These are ultrasonic frequencies you can't hear, but if they are not removed, they can cause problems for your amplifier, sometimes even creating audible distortion. The job of the analog low pass filter is to gently remove this ultrasonic noise, leaving only the pure audio signal. The design here is a balancing act. A filter that's too aggressive can smear musical details, while one that's too gentle can leave a digital glare or harshness. A well designed analog filter is key to getting a sound that is both detailed and smooth. Finally, we come to what is arguably the most overlooked yet fundamental component of all, the power supply. The analog output stage is an active circuit. It needs clean, stable DC power to work. The power supply is the foundation for the entire analog performance. You can have the best DAC chip and the most sophisticated output stage, but if you feed it dirty power, the performance will be compromised. Think of the analog stage as a surgical team in a sterile operating room. A noisy power supply is like leaving the doors open to a dusty construction site. This electrical noise can leak into the sensitive circuitry, showing up as hum or hiss, and it can also cause the power to sag during loud musical passages, compressing the dynamics and making the music sound flat and lifeless. This is why, when you look inside a high end DAC, you often see a huge amount of space dedicated to the power supply. You'll find big, heavy transformers, massive filter capacitors, and multiple stages of power regulation, often with totally separate power supplies for the digital and analog sections. This intense focus on isolation isn't for show, it's a fundamental requirement for letting the analog stage perform at its absolute peak, free from the corrupting influence of noise. Okay, we've been deep in the technical weeds, but what does this actually mean for you, the person who just wants to enjoy their music? How does this help you build a better sounding system? First, you now have the answer to a common audio puzzle. Why can a DAC with a top of the line chip sound mediocre while another older chip sounds magical? The answer is almost always in the analog output stage. A manufacturer might use a flagship ESS chip for marketing points, but then cut corners on everything else to hit a price. They might use a single budget op amp and a cheap wall wart power supply. The result? A DAC that measures well but sounds thin, brittle, and uninvolving. The potential of that great chip is completely bottlenecked. Conversely, a company might choose a more modest DAC chip but pour their budget into a fully discrete Class A output stage with a massive linear power supply. The specs might not be as flashy, but the listening experience can be vastly superior, more dynamic, textured, and musically satisfying. They prioritized analog engineering over digital specs. This knowledge helps you become an informed shopper. Look beyond the chip model number. Read the manufacturer's description carefully. Are they only talking about the DAC chip, or are they proudly describing the other parts? Look for keywords like fully discrete, output stage, Class A, custom IV conversion, film capacitors, or an oversized linear power supply. If a company invested in these areas, they will tell you about it. Look at pictures of the inside. Does it look empty with just a singular chip and a few tiny parts? Or do you see thoughtful engineering, dedicated stages, quality components, clean board layout, proper shielding, or carefully separated digital analog sections? The internal design often tells you more about priorities than the chip itself. And this is where pricing starts to make sense. Why does one DAC cost $200 while another using the same chip costs $2,000? It's rarely about the chip. It's about everything wrapped around it. Custom IV stages, low noise power regulation, precision components, isolation layout, and in some cases, discrete Class A circuitry or robust linear power supplies. Note though, not every high-end DAC uses huge transformers or massive capacitors. Take Benchmark, or RME or Chord as perfect examples. Their performance comes from extremely sophisticated engineering, ultra low noise power stages, and custom digital architectures. The point is this: you're paying for engineering, not size. A well executed analog stage, whether compact or physically substantial, is what elevates the sound. This isn't snake oil, it's a direct link between real engineering investment and real sonic performance. Ultimately, this frees you from the misleading marketing or just rants on forums about measurements or claims on the spec sheet. It helps you understand that DACs sound because of deliberate engineering choices made in the analog domain. So we started with the common belief that the DAC chip is everything. Now we know the truth. While the chip reads the notes, it's the analog output stage that breathes life into the performance. It's the IV converter, the amplification stage, the filter, and the power supply that provide the heart and soul of your sound. If you want to unlock the next layer of DAC performance, check out the videos on the screen. One breaks down DAC filter modes in a way that finally makes sense, and the other shows you how to match your DAC to your amplifier for the best possible sound. Start with whichever one your curiosity pulls you toward, and I'll see you in the next one.